the continuation, local behavior of functions. So I didn't prepare my screen, so I do it now. Right, so we mainly just are already there, right? So what do we want to do? So we say that the point of a function, for a function, is the critical point of order k if the first k derivatives at the point a are 0, but the k plus first one is not. So for example, critical point of order 1 was our favorite one, and if we suppose that the next one is not 0, then it must be either bigger or 0 or smaller of 0, right? And we expect the function to be having continuous derivatives of the k plus first order. That's important, right? It must be in ck plus 1. Otherwise, what I will be talking about wouldn't work. So let's see. So definitely, in that case, we can write down the Taylor expansion, right? So the Taylor expansion with the remainder is of this kind. So we have got f at the point x, which is close to a. So let me draw the picture. Interesting. So if we have the function like this, and here is a, here is x, then we know that the function will have 0 derivative up to order k, and at the same time it will be having positive the next derivative, right? So we know that then the Taylor polynomial with remainder will be fa, that's the zeros order part. Then there is just a bunch of zeros, and then there comes the remainder, the k plus first term. And this is of this kind where c is something in the middle here, right? So this is the c. We know that there is a c somewhere between a and x, giving us this. But because we expect that the k plus first derivative is continuous and it was bigger than 0 at a, so here it was bigger than 0, then it must be also bigger than 0 on some reasonably small neighborhood. So we know that for x close enough, the second derivative, or the k plus first derivative, will be bigger than 0 for all such possible c's, right? So if x is close enough to a, then whatever c we take, we know by the continuity that the value will be bigger than 0. And then, therefore, we see that the function has got a local minimum at the point a, right? And you see the power, because if we didn't expect that it's continuous, we couldn't make the conclusion, right? Because the error is there. But we can control the error, we can control the sign of the error, and therefore we know how it works. So that's perfect. And of course, if it was less than 0, it would be maximum. Well, let's go on. Imagine now how the functions behave. So that's what I was trying to talk about last time too, just talking about the fact whether the function is above or below the tangent line, right? So we say that the function is concave if its graph lies completely below the tangent. So this is a concave function, and convex function is if it's the opposite case. So if it's concave, it means that the value of x is always smaller than the value on the linear approximation. So it's this one. And convex means that it will be just the other way around. And we say that it's convex or concave on an interval if it's true in all of the points. And now again, look at the second order Taylor expansion with the remainder, right? So up to the linear term, we've got the derivative at a and value at a, but then there is some c. So you see, that the first part here was exactly the same as what we compare with, and you see that it's the sign of the second derivative which decides whether it's concave or convex. And in pictures you can see it nicely here. So this is the part where the graph is below the tangent, so it's concave. The derivative must be less than 0, so the slope is falling down. If the slope is going up, so the derivative, the second derivative, is bigger than 0, then it's convex. And to jump from convex to concave, or the other way around, we must come through an inflection point. And the inflection points are simply those where or potentially those where the second derivative is 0. And you see, if we take the expansion of the third order, then it just gives you some explanation. So I think I don't have to go further with that. And the last thing, to be able to draw a reasonable, say, approximating picture of a function behavior, is to deal with asymptotes. So that means that you try to decide how the function would behave if you grow with the argument above, so beyond the limits, right? So there are two types of asymptotes. One of them is an asymptote with an improper point, so it's at infinity, and that would be an asymptote where you simply have something like a function, right? So say such a function, and imagine that the function would be, when growing to infinity, it would be more and more close to the line. And so it could oscillate above and below, but going to infinity, it would behave roughly as the line. And then we say that it has got the asymptote, which is given by the line. And how to get it? Well, so we take a general formula for a line, and we want that the function behaves exactly as the line in the infinity. So it means that the limit for x going to infinity should be 0. And that's the so-called asymptote with a slope. And if such an asymptote exists, if such a limit exists, then definitely, because this is a constant, b is a constant, right? So it's equivalent to this. So having an asymptote with slope must mean that the limit of fx minus ax exists and is equal to some number, some real number b. And consequently, if we now divide everything by x, then we get that this is again equivalent to the fact that the limit of the quotient fx over x must be a, right? So that's very straightforward. You don't need any smart ideas to follow that, but it's useful. It just tells you how the function behaves. And so you can always find such an asymptote. Like here is an example. If you take such a function, then you simply differentiate and you find out how it behaves, right? So the first derivative, the second derivative, and you get one minimum here and one maximum here. That will be the two critical points. And then there will be the asymptote, which is the dashed line. And you compute it very easily in a straightforward way. At the same time, it shows also the second type of asymptotes, and that's in the points where the function has got infinite limits from the right or left or both, right? So if there is an infinite limit approaching a point from, say, right, then we say that there is this line as an asymptote, but we also want that the other is either the same infinite limit or it goes down, right, like here. So here we have two asymptotes. One is now doesn't work. we've got two asymptotes here. Well, one is the dashed one, that's an asymptote with slope, and the other one is the y-axis, which is the other type of asymptote. So that's it. So with these tools, you can, for each function where you can compute the derivatives, either numerically or explicitly, you can just get the message how the behavior of the function is on all the interval where it's defined. So have a nice rest of the week. See you soon in some way.